Welcome to this video on solving problems using force and torque. We've solved a lot of problems in earlier videos using force by using net force statements and force diagrams and all those sorts of things, Newton's second law, in order to calculate various things, acceleration, so forth. But now that we're introducing this idea of torque, we're also going to look at how torque can be employed to solve problems as well. And sometimes I can use both to solve for certain problems. And so in this video, the main goal of this video is just to show how we can identify forces that are also causing torques on an object and how you could use either or to solve the problem or both, depending on what you're given and what you're looking for. So let's just first take a quick look here at the idea of forces that we would solve for problems using net force statements. And we know that the net force is equal to mass of the object times the acceleration, or we can look at it as the sum of the forces that are acting on the object. Those are both true statements, and they both would equal the net force, which would equal the mass times the acceleration. Now, we oftentimes break our force statements into horizontal forces or vertical forces. Some people call them perpendicular and parallel. It just depends on the measurement system that you're looking at. Now, torque, as we've just started to identify in the last few videos, a net torque, right, could be solved in two different ways. We can have the moment of inertia, which we still have to investigate a lot more, times the angular acceleration. But more useful in this situation, I'm going to use the force that's being applied at a particular point times the position that that force is applied at. The angle between the two obviously is represented in the cross product. Okay. In this situation over here, what we're going to do is we're going to look at clockwise versus counterclockwise. And I'm just going to symbolize that with CCW, counterclockwise. But these are not the same separate statements as horizontal and vertical. This would be like saying right and left in the same dimension, right? It's a little bit different. Usually we're going to symbolize clockwise with a negative and counterclockwise with a positive. Now, if we think about horizontal, we would symbolize, maybe to the right or to the left with, I'm just going to pick positive for right, negative for left. Vertical, obviously, we would have up and down, and that, I'm going to pick, just a traditional system would be up is positive, down is negative. But for torque, we only have one considered dimension, and that is just the rotational dimension, and we're going to say clockwise or counterclockwise matters. So we don't necessarily have to break it up into horizontal and vertical first. We really just have to identify whether that torque is going to be, or that force is going to cause a clockwise or a counterclockwise spin. Okay. So let's go ahead and look at a very traditional problem here, and we'll employ each of these systems to set up how we might go about solving for various variables. This is a famous kind of problem where we're looking at a ladder leaning against a wall, and the ladder is propped up and there's forces acting on it. Now, when we draw a force diagram, we've always been looking at the forces all acting at the center of mass. This is with the free body diagram. But here with torque diagrams, we're going to look at the origin of force. So the location where the force is acting relative to the center of mass or axis of rotation. Now, axis of rotation is more important than center of mass in most of these cases. Now, if you were to fling an object into the air, it would rotate about its center of mass, and so the axis of rotation is the center of mass. But I'm going to say, rather just pick an axis of rotation that we'll look at here. So here's this ladder leaning against the wall. Let's identify all the forces that are acting upon it. Okay, first of all, I'm going to say that the weight of the ladder, or the force of gravity pulling the ladder down, is going to act at the center of mass of the ladder, which if the ladder is, sort of a uniform rectangular-ish shape, it's going to act at the geometric center, so right here. So this is my m times g vector. Okay. The ladder is pushing down on the floor is pushing back up on the ladder. I'm going to call this normal force from the ground, N sub g. And then I have a normal force pushing out from the wall, which I'm going to call normal sub w. This, obviously, normal means perpendicular, and it's always perpendicular to the interacting surfaces. So I should have something that looks like that. In addition to this, to keep the ladder from slipping down the wall, I would have a frictional force pointing up, which I'm going to call friction sub W. And on this one, I'm going to have, from the ladder slipping out to the right, I'm going to have frictional force on the ground. So these are the 4 or 5 forces that are acting on this object. Now, I'm going to use a reference frame that has positive x in this direction and positive y pointing up. Okay. Now I know some people are against calling this x and y. That's just what I'm doing in this video. So this would be positive, this would be positive, this would be negative, this would be positive, this would be negative. Now they're not all in the same dimension, so what I'm going to do is I'm going to write horizontal net and the vertical net force. These should be fairly straightforward. So let's start with the horizontal net force. Okay, I have this one and this one. So I'm going to have normal force from the wall minus the friction from the ground is going to be equal to 0, because here I'm hoping that my ladder is not slipping. Now I'm going to analyze the vertical forces. I have this friction from the wall, okay, plus the normal force from the ground, minus the weight of the ladder. That all equals 0. It's not slipping. So there we go, and I could solve for whatever I needed to if I had enough information. Now sometimes you're not going to have enough information to solve using this method, and so what you're going to do is look at it from the torque perspective. And so let's identify which forces are causing a torque and if they're clockwise or counterclockwise. Well, you come to your picture, and in order to decide if they're going to cause this thing to rotate clockwise or counterclockwise, I first and foremost have to identify an axis of rotation. If you don't identify an axis of rotation, then the problem is stuck and you'd have to figure something else out. So the way that you identify the axis of rotation depends on 2 things. It depends on, first, what you're solving for. What are you looking for? Okay, that's the first thing to consider. And once you've considered that, then you decide to choose an axis of rotation that eliminates the most terms possible. Now that would just be because you don't want the problem to take 6 years to solve or have lots more possibilities for errors. Okay, so first I have to know what I'm solving for so I don't accidentally eliminate it when I try to eliminate terms. Now the way that we eliminate terms in a torque setup is if the force is acting at a certain position and that position is at the axis of rotation, then of course R is 0, because remember this is the distance from the axis of rotation to the force. So if there's no distance, then there's no torque provided by that specific force. Okay, so if you pick a pivot point where you make R 0 for certain forces, that eliminates them. But you don't want to do that if you're solving for something at that pivot point. Okay, so the pivot point, is it arbitrary? Yes, it is. When you're solving a problem, it is. Okay, so I look here. Now, I didn't identify what I'm solving for, so I'm going to pick something. I'm going to say you want to know this term. That's what they've asked you to solve for. What's the force that the wall is pushing back on the ladder with? Okay, so that means don't pick this as the pivot point, otherwise R will be 0 for the normal force from the wall, and that will cancel that term out of your net torque statement. So I'm not going to choose this as the pivot or the axis of rotation. Those are the same thing. Now, if I pick this right here, I'd eliminate mg as a force causing a torque, but then I would still have 1, 2 other forces acting. If I pick this point over here, and I would have this force, excuse me, so I'd have 1, 2, and 3 forces acting if I pick this as my axis of rotation. So I'm not going to do that. I don't want that to be the axis of rotation. So if I pick this point over here, I eliminate 2 forces from the net torque statement, okay? And then I have 1, 2, 3 forces that I have to use to solve for, whereas if I picked mg, I would have 4 that would be in my term. So that's my choice that I use most of the time. So let's do that. Let's set that up as our problem. So what I'm going to do here is I'm going to say that my net torque statement is going to be equal to each of these forces times their position times the angle at which they're acting. Okay, so here's my pivot, meaning this force and this force are not causing a torque. Don't have to worry about those whatsoever. Okay, so I'll start up here. Now, instead of doing positives and negatives based on how in what direction they're pointing, I'm going to choose positive and negatives this time to decide what direction would that force cause the object to rotate, counterclockwise or clockwise. Okay, so this is my pivot, remember, over here. So let's label this as the pivot or the axis of rotation. Okay, this normal force, if it's pushing this way, it would cause the ladder to rotate in the clockwise direction relative to this. Okay, so that's clockwise, which I'm going to make negative. So I'm going to say this normal force is negative. Okay, this frictional force is also going to cause it to rotate clockwise. It's kind of at a weird angle relative to the circle that this would map out. So that's also going to be clockwise. Now the ladder's weight, you can see is pulling it counterclockwise. Relative to this point, it's pulling it down this way. If you think of this as a giant lever that's going to get pulled down, and so I'm going to make this one positive. So when I'm listing out my torques, I have to list the torques as being negative if they're causing clockwise rotation, and positive if they're causing counterclockwise rotation. Okay, so let's start with this one. Remember, we're saying F times R. I won't put the angles in yet. So I'm going to say the F here is mg, and the R is half the length of the ladder. So let's say that they gave us that information too, which I didn't put in the beginning, and we're going to say that the ladder's length is L. So it's acting at L over 2 from the pivot point. Okay, so we've got that, and it's a positive term. Now I need to put the cross product in here, so the cross product sign, so I don't forget that I need to include an angle. Okay, now I'm going to subtract these two terms, so that minus this force or friction from the wall, so I'm going to call that F sub W, and the R value for that, sorry I keep forgetting to put my cross product in here, the R value for that is L, because that's where the force is acting relative to the center of pivot or the axis of rotation. Okay, minus the normal force from the wall, which is also acting at L distance from the rotation. That all sums to 0 because it's not rotating, right? It's all at equilibrium. So now I have this system set up here where I have mg cross L over 2 minus force of friction from the wall cross L minus normal force from the wall cross L. What I'm going to do in the next video, because this one's already long enough, is I'm going to take a look at how do you determine the angle, okay? So how do I get rid of the cross product and put in the angles here, which remember is going to be the sine of the angle between the force and the position vector. we'll pick up on that in the next video.